Hello, everyone. This video is about the definition of a multiplicity of an eigenvalue and its importance. Let's start by recalling the example we discussed in the previous videos, where there was a matrix, a 3 by 3 matrix, of which we computed the characteristic polynomial, which was minus lambda minus 2 squared times lambda plus 6. The conclusion we drew from that characteristic polynomial was that the eigenvalues were lambda equals 2 and lambda equals minus 6. However, we didn't comment on the importance of this exponent here. In fact, that exponent is called the multiplicity of the corresponding eigenvalue. So that's the multiplicity of the eigenvalue lambda equals 2. And in fact, here's the definition. If any number lambda naught is an eigenvalue, then to be an eigenvalue, it means that there's a factor lambda minus lambda naught inside the characteristic polynomial. The exponent of that factor is what we call the multiplicity. So in this case here, we say exactly that the multiplicity of the eigenvalues u is 2, and the multiplicity of the eigenvalue minus 6 is 1, because there's a hidden exponent to the first up here to that fact. Let's have a look at why multiplicity is important and what exactly is the role that it plays. So we'll pursue this example further by computing the eigenspaces of the eigenvalues we computed. So let's start with the 2 eigenspace. Remember that the 2 eigenspace is the solution set of a minus 2i times v equals 0. So let's start by computing a minus 2i. This becomes matrix with zeros here, and then it becomes minus 4, minus 4, minus 4, minus 4. Now, to compute the 2 eigenspace, which is the null space of a minus 2i, we can solve the linear system homogeneous associated with a minus 2i. The way we would do that is by row reducing this matrix to an echelon form, but we can argue alternatively, and sometimes this could end up in a shortcut in the following way. Well, we can look at the rank of a minus 2i, and I claim that this rank is 1, because the rank is the number of linearly independent columns. Now, clearly, there is at least one linearly independent column, for example, this one. But then if I take any 2 columns here, they are not linearly independent. So the ranking is 1, which means that the nullity of a minus 2i, which is equal to the dimension of the null space a minus 2i, is equal to the number of columns minus the rank, which is 2. So the eigenspace has dimension 2. To find and completely determine the eigenspace, our goal is to find 2 generators for the null space of a minus 2i. And of course, this is completely equivalent to solving the linear system, but in this case, we can maybe try and do it by staring at the matrix a minus 2i. For example, the vector 1, 0, 0, when I multiply it by the matrix A, extracts the first column, but the first column is 0, 0, 0. So that is a solution to the homogeneous linear system. Another way to get a solution to this linear system is, for example, adding the second column, subtracting the second column from the third. I could do something like this, or subtracting the third column from the second. In fact, it's very straightforward to check that if I multiply that by my matrix A, you don't have to compute. You just realize from here that this is exactly A2 minus A3, which is 0, where A1, A2, and A3 are the columns of matrix. So we found two generators, 1, 0, 0, and 0, 1, minus 1. They're linearly independent, so they're a basis for the null space because the null space has dimension 2. And a system of generator with the same number of vectors as the dimension is a basis. In other words, we found a basis for the eigenspace, and we computed its dimension. It's an alternative way from solving the linear system. If we went the usual way to solve the linear system, we would have first found generators and then counted them to establish the dimension. Here we did the opposite. We computed the rank first, and then we found a corresponding basis. Let's have a look at the other eigenspace. There still is the -6 eigenspace. Again, we want to find we want to understand the null space of A plus 6i, and maybe the first thing that one could do is, if you use this alternative method, try to compute the rank. This is the nullity of A plus 6i, which is 3 minus its rank. A plus 6i. Now the rank of this matrix, I claim, is equal to 2. For example, because these two columns are linearly independent, but not all three of them are linearly independent because these two columns are one the opposite of the other. So the rank is 2, therefore the dimension of the null space should be equal to 1. Having a one-dimensional eigenspace like this implies that it's enough for us to find one vector that belongs to the null space of A plus 6i. And by just staring at the matrix, we can understand that if I take the sum of the second and third column, I get exactly 0, the 0 vector. So the vector 0, 1, 1 belongs to the null space of A plus 6i, but since this null space is dimension 1, 0, 1, 1 is a basis of that null space, which is the -6 eigenspace. This is an alternative way, and it relies a little bit on intuition, but sometimes it can make your life easier. So it's good to know that you can solve the problems like this. Some other times you want to be safer, and so then you just solve the linear system, the homogeneous linear system, as we've been doing. Let me just wrap up the data we concluded. The basis is 0, 0, 1, 1, and the dimension is 1. Summarizing this example, we have eigenvalue 2 with multiplicity 2 and eigenvalue -6 with multiplicity 1. And the dimension of the corresponding eigenspace was 2 for eigenvalue 2 and 1 for eigenvalue -6. So one would suspect that there's some relation between the multiplicities and the dimension of the eigenspaces. In fact, there is, but the relation is not what's suggested by this example. It's not true that the multiplicity is always equal to the dimension of the eigenspace, but what is true is that the multiplicity is always bigger than or equal to, and, well, in the case when it's 1, it's actually equal. Here's the theorem, which is exactly what I just said in this example. For any eigenvalue of A, then the dimension of the eigenspace of that eigenvalue, I should say it's always at least 1. You can't have 0 eigenspaces. And it's always less than the multiplicity of your eigenvector. So just a little remark. If the multiplicity of a certain eigenvalue is equal to 1, then you know that the dimension of the corresponding eigenspace must be exactly equal to 1, because eigenspaces have dimension at least 1, and they are smaller than the multiplicity. However, if, just like in our example, we had the multiplicity equal to 2, the only thing you can conclude is that the dimension of the corresponding eigenspace is less than or equal than 2. That's to illustrate the second statement here. Maybe I'll clean it up. Multiplicity of lambda is equal to 2, then the dimension of the eigenspace, it could be 1 or it could be 2. Here's an example of that. There's a upper triangular matrix. The characteristic polynomial of an upper triangular matrix is actually very simple to compute, because if this is your matrix A, I can write A minus lambda, the identity, by just subtracting lambda here to all of the diagonal entries. In other words, A minus lambda, the identity, is also upper triangular. So when I compute P minus lambda, that's just the product of all these. And I have 1 minus lambda times 2 minus lambda, but 2 is repeated 1, 2, and 3 times. 5 minus lambda. That's my characteristic polynomial. So my possible eigenvalues are 1, 2, or 5, with multiplicities respectively 1, 3, and 5. Oops, this is a square, so 5 is multiplicity 2. So what I know about the corresponding eigenspace is that the dimension of the one eigenspace is 1, exactly 1. The dimension of the 2 eigenspace is less than or equal than 3. I can't say anything more. And likewise, the dimension of the 5 eigenspace is less than or equal than 2. And, well, by the very definitions, we also know that they're bigger than or equal than 1. Okay. I'll see you in the next video.